Is on Thursday. Okay, so as I said, the planes is the last topic, but we'll keep going, and tomorrow we'll have a review of some kind. Okay, so we're studying functions of two variables right now, and trying to avoid for the time being calculus in the narrow sense of the word. So trying to find indirect ways of reducing the this kind of three-dimensional situation into two-dimensional situations with only two variables in order to be able to apply calculus 1 at some point. So that is a little bit messy here, but we'll try to make it up. So we are skipping this. We're skipping where we're done more or less with the domains now. And now we're looking at once again what our graphs are made of, and how to make them pretty much of curves. Okay, so let me first make clear what we mean by graphs, just in case. So a function. So given a function of the variables is equal to f of x, y, its graph is a set in R3 of all triples x, y, f of x, y. Okay? All possible triples. So, function, so the graph, that's what the graph is. In dimension 1, it was the set of all doubles, pairs, x, f of x, that's what we had in dimension 2, and now this is what we have in dimension 3. So, okay, so that is generically is a surface. Why generically? Because if your function is, there might be weird functions. They may have weird domains, including a domain that is just say a straight line. Then you're not going to produce a surface. So, but probably it is a surface. Okay, and then there are also discontinuities and so on. So. Surface might be a way to describe it in general, what happens typically. Okay, so studying surfaces is hard. In fact, that is how you would start studying surfaces. You study them initially as graphs of functions of two variables. So, for example, we are not right now in the position to study the surface of the Earth or of the sphere, because it does not satisfy the vertical line test, but this is the starting point. Okay, so generically, you can still split it in half, just like with a circle some time ago, and you can study one half and the other half, and then collect the information together into one. Okay, so let's once again go back to this example of f of xy equal xy, a nonlinear function, and what we did last time was to try to restrict the domain, specifically to a curve. To a curve that is a curve will be a relation between x and y, right? And as such, we are eliminating one of the variables. So y solved for x, x solved for y. We substitute into our function, and then we're done. You don't really want to go all the way with all the possible curves. And we did it. We initially started with example y equal x, but the most typically is those curves are really straight lines. So straight lines that we pick specifically are x equals say a, and y equal b. So all possible on the xy plane. This is our domain, and we're picking either a horizontal line or vertical line. So this is x equal a, and this is y equal b. Okay, so this is the, let's be clear, we're looking at the space of inputs, also known as domain, but sometimes the terminology is a little bit screwed up because the domain is where the function is defined, and we're the potential out, and then you check out all potential inputs, and then you throw some of them when you have like division both by zero or something like that. So the space of inputs, potential inputs, is the whole plane, and then the space of outputs, we'll get to that, is R. So space of inputs R2, and space of outputs is R. Okay. So, and we are restricting our domain by a line, which eliminates one of the variables in a very specific way here, right? So, so in that particular case, you have in the first case we have f of x. Now let's take the second one, xb equal to xb. Okay, I replace y with b, and I have my formula of a function of one variable. So I could, if I like, I could just to make that point, I can rewrite it as specifically as say g of x equal to bx. Okay, it is a straight line. Once again. Okay, so the point here is then unfortunately there are infinitely many of those. The vertical lines, infinitely many horizontal lines, and so there will be infinitely many curves, which is hard, but then that's what the surface is. It's made of infinitely many curves. Okay, so and these are especially in particular. So so they all straight lines as we discovered yesterday. So in fact I could plot them. This is x against z, and with b varies, right? B, that's the value of y, it varies, and so I will end up with a bunch of straight lines. So they roughly look like these, including negative ones as well, and including horizontal one as well. Okay, so the vertical line is out, but the rest are already. So these are the lines. So this is not very revealing. We only know that a line like that will be contained in the graph, in that surface. It's made of surfaces, right? So consider the fact that if I take all of those green lines, they do cover the whole domain. Okay, which means that every point on the graph, okay, every point on the graph will be taken care of. It will belong to one of these lines. Just to be specific, every point on the graph lies on what? Or rather, on one of these lines. Okay, by which I mean these lines, but they are in the three-dimensional space. Okay, so here they lie, the graph lies in three-dimensional space x, y, z, and these are two, so the y dimension will have it to be taken care of. Okay, similarly for if I fix the value of x, I have vertical lines. The picture is almost identical. Well, it is actually entirely identical. So the variables will be y, and so x is fixed, so y remains a variable. Okay, so I have a bunch of straight lines once again with all possible slopes. So all slopes. Okay, so once again, it turns out that because of the symmetry between x and y, so certainly we can split it this way. Or we can split it that way. Remember, so we are limiting the domain. It means cutting the surface with a vertical plane. Okay, so suppose this is my surface right here, a three-dimensional thing, and then I'm cutting it with a vertical line. So in this particular case, if our axes are like this. So x, y, z. So I'm talking about this plane being, say, y equal b. Okay. On the other hand, I could go the other way and have cut it this way. And that is x equal a. Okay. Either way, the end result is in the former case, or in either case, it will be a curve. And then so curves. Well, we were lucky with straight lines here, but these are curves in general. And then use calculus 1. Not even parametric curves. These will be not just curves, these are actually graphs of functions of one variable. Okay, so everything applies. We're going to do that very shortly. Once again, using calculus 1, functions of one variable, derivatives of functions of one variable, in order to study these cuts, these curves, and they're located directly in a particular way along the surface. Okay, so once again, into many of them. Okay, so I could have another one going like this, and I could have another one going like that, depending on the value of a or b that I choose. Okay, so before we get to calculus 1, there is another way to study graphs of functions of variables by looking at curves. So there are other ways to produce curves other than restricting the domain. Okay, so it doesn't have to be restricting the domain. Does not have to be necessarily along the axis, which is what we just did. So remember, the example we started with was y equal x, and indeed you might choose different directions not along the axis. It might be very revealing. In fact, that was a big point that was made early on to realize that this curve is in fact not a straight line because where is it? I plugged in a y equal x somewhere, and I ended up with x squared. Remember that one? For some reason I can't see it here. And it was a parabola right here. Okay, so to discover that there's a parabola, if you cut it along the line, along the axis, you will end up with nothing but, you might end up with, you might be missing something. And this one reveals that there is actually a parabola. And that's why it's called hyperbolic parabola. So another ways to produce curves is how do we produce those hyperbolas? Here it is. Yeah, see those hyperbolas. So how do we produce them? You see hyperbolas, right? Hyperbola. So this is a parabola. That is another parabola, but this one is a hyperbola. You see this one? This hyperbola lies within this plane. Okay, so what happened here? We cut the graph, the surface with the horizontal plane this time. So we have been cutting it with vertical planes. So other than vertical planes. Okay, so imagine if you have some kind of bowl of cheese, or then you can cut it like this, you can cut it like that, and you can cut it like this horizontally. So other than is horizontal planes. Okay, and so what it means is that we restrict instead of the domain, we restrict the range. Right? the vertical dimension is z, it is the range, and we restrict it. It is much easier because dimension is 1. So domain is 2-dimensional, range is 1-dimensional. So how do you restrict the range? We pick a value. So pick a value, and that's it. So restricting to one single value. Okay, so here we have generically the most typical ways to do restricting the domain is x equal a, b is equal to c, right? So this is the most common but not unique. This one is almost unique. You say z equals c. Okay, so algebraically this actually looks very similar, but it does produce very different results. As you can see, it produced here not just one but many hyperbolas. This is also hyperbolas. That is hyperbola. A bunch of hyperbolas. So let me do that. So if I have my f of xy equal xy, that is the value of z, the output. So I solve for I set value of z as we did it a little bit of that yesterday. So you can just set z equals say 0. Then you have, and then you don't do anything much else. Then you have xy equal to 0, and remember what the result was. What?
Oh, it was just the 2 x's?
2 x's, right. So once again, clearly we should understand that what we are after, we're trying to find all of those x and y's that satisfy the equation, which actually certainly is not very new or new at all. What do we call these? What do we call these? Not specifically, but the type of.
The type of curve?
Type of equation, no. We know that the second one will produce a parabola, hyperbola. And the rest are actually hyperbolas. But the equation xy equal 1, for example, what do we call it? How about x squared plus y squared is equal to 1? What's the generic term?
Binomial?
No, more general. No, one is circle, one is hyperbola. Yes, it is a relation between x and y. Yes, but yes.
Is it a quadratic?
No.
Or it's some kind of
No. It is a relation between x and y, but it's not a function. So.
Equation?
What kind of equation? Okay, so let me actually do this. So if x is equal to 1, then I could do this. Y is equal to 1 over x. What's the difference? What did I do?
You made y depend on x?
Right, so I turned in a relation that is where x and y are equal. X equal to 1, there's not, x does not depend on y does not depend on x. I turn it into a function, right? So.
It's a parametric equation?
No, it's not parametric actually, no. You saw these in calculus 1. I'm just trying to see if you remember the term. The term is very simple. It's implicit, right, implicit. So this is implicit while this is explicit. Okay, so it is a relation, and a relation could be explicit. Y depends on x. You plug in x into the formula, you compute, and you have y. That's explicit, and then implicit is the relation is there, but you might not be able to see it directly. And as it is not a trivial transition because of the vertical line test. You won't be able always to do this, right? Because for example, with the circle, you cannot solve for x and just or for y and just be done with it because there will be plus or minus, and so the implicitness won't go away entirely. And that is a typical situation, not very, really typical situation now in comparison to Calculus 1, where it was just a few curves, and we tried to sort of steer around them because we would have to convert them into functions in order to study them with Calculus 1 tools. Now we don't have this luxury because as you can see, what we're looking at is a bunch of implicit curves. All of these I'm producing one by one, a bunch of implicit curves. Okay, so how? I'm just cutting the surface of my my graph. I'm cutting it with horizontal planes, and each of them will give me, generally speaking, an implicit curve. Okay, so and it's easy to see those and these, and some entirely unpredictable functions might come up. Okay, so let me. So these are the two very typical ones. The equation of the line, another. So you remember that ax plus by plus c is equal to 0. That's implicit equation of the straight line. What else? These are the main ones, I suppose. There's a circle, there's ellipse, a hyperbola, a bunch of them. Now the difficulty is, even though that part is on the left is the same, we do have infinitely many of them. So let's just plot them, and hopefully we'll see a pattern. So we start with, we take our xy plane and we plot all of these. I will start with the first one. So this one, so it will be just going along the axes. So it is also a good idea to look carefully at this part, at the value of z, and attach it a mark to the curve, which is really that's a weird curve that indicates the value of z. So for example, z here equal to 0. Okay. So I'm trying to, let's do one more, and then I'm going with the next one, xy equal to 1, and so it will be 2 hyperbolas, this one and that one. So once again, it is z equal 1 and z equal 1. So I'm trying to use different color as well as use the markings. Okay, so the point being that remember that value of z is the elevation. So what we're doing, we're literally mapping the surface. So remember that metaphor, function of two variables represents the terrain, and then whatever the source of it is, and then we're trying to produce a map of it, and one way to do it is like this. So, what we just did, I didn't actually plot it, but straight lines or those parabolas. Remember those parabolas? They are like elevation maps, and so this one, if I go from different initial location, that's what we're talking about here. From initial location, I go, for example, wait a minute, so let's say x and y, suppose this is x, this is y, so maybe y would be east. So if I go east, that indicates how fast I'm going to be climbing, okay? And here if I go south from a different locations, this is how fast I will be climbing. And this one, now we're doing a different one. We're not, the elevation remains the same. Okay, so in fact, what we're interested in, if we continue on the same elevation, where are we going to end up? Okay, so as you can see, so each curve is the same elevation, and then I certainly can get from this to this one. They're disconnected, but they're still at the same elevation, and then they just plot many of them. And you remember that is how many maps are made, exactly in this fashion. So if I do one more, xy is equal to 2. So it is y equal x over 2, so It's looser. So it still has those asymptotes. So it's equal to 2, and then negative values will give me will be on the other in the other two quarters. So for example, xy equal -1 will be this, and z is equal to -4. Z is equal to -4. Okay, the z equals equal to -2. Colors. Black. So this will be z equal -2, z equal -2. So that is a map. Okay, that's what a map is. So you need some imagination to understand what it behaves like. It is very tempting to go straight here. Why try to imagine? Why do follow all of these indirect methods when you can plot the graph and have the whole thing right away? And you can turn it around and look underneath if you like. Okay, so it turns out, well, it helps with high dimensions. So just better. We will see that shortly. How this is the method for studying functions, all functions of many variables, including not only 2 but 3 and higher and more variables, and that is the reduction to lower dimension is the method that I want you to learn. So here we are reducing the surface to curves, to a bunch of curves, and then we'll do the same with a function of 3 variables, and that would not then be as easy. And you cannot function of 3 variables, you cannot plot. Okay, so function of 2 variables, you plot it as surface, and so you can see it at once, the whole thing. Function of 3 variables, it lives in the 4-dimensional space. We cannot plot it anyway. Higher, more dimensions, it will only get getting worse. But if you can reduce it to lower dimensions, that helps you to understand what's going on. Typically, it is once again, I want to emphasize that this is the fixing one of the variables is the best way to handle it, but this one is also very, very effective. So then what does it, let's imagine for a moment that we don't know what the surface looks like. So how do we reassemble it from this information? Because this is really old tech, 500 or whatever years ago. How they didn't have Excel. They had a piece of paper, and then on the piece of paper they withdrew, and then they had to use the imagination to figure out what the graph looks like on the surface. So different elevations, and literally you can just do it this way. You plot 3D. Well, let me, for a change, just put it in the different direction so we can easier align things here. So in other words, I could repeat this picture. Let me try to repeat this picture. At least some of them, like this, for example. Okay, so that's the picture. I just took my my graph and put it, that is a 2-dimensional xy plane, and then put in the 3-dimensional xyz space. Okay, then what's supposed to happen is I take the same picture and then I start to lift each of these curves to how high. That's how high. It has, everyone is marked with the elevation, and you just lift it. So for example, this one will have to be lifted by 1, like this. So it is lifted, preserving the same exact shape. It will be located at height 1, like this. Okay, so whatever was drawn on the xy plane, well, now is hovering about that picture. The easiest one in the middle, because that one is not going anywhere. So this is equal 1, and it remains on the same level. But on the other end, once again, that picture, that hyperbola will lift it like this. And once again, what is on the xy plane is not important anymore, because that is, so I drew this in a thick line, so to emphasize that actually the line that we have produced, and that line, the curve, is a part of the surface. Okay, so right now we have the cross on the xy plane, and we have these two hyperbolas, but you can imagine what happens if I now move on to So this is equal 1, is equal 2. Is equal to this one. So same, it's drawn over here, but this time I lifted by 2 units. So like this. So it will be the same thing, only lying higher than the first one, and that will be like this. Okay? The hope is that you just look what's happening here and tell what's going on. So starting with like 2 lines like this, then higher and farther in diagonal direction, it is still a kind of parabola, and then higher yet and more into the diagonal direction, another hyperbola, and you can kind of start to imagine what the surface might look like. And the more curves you draw like this and translate them vertically, more and more you understand what it looks like, right? It starts to create a shape, and it is made of those surfaces. Okay, imagine that they are being transformed one into the next in a continuous manner. So the green one into blue one into the purple one, and then you have a surface. Okay, the difference is what happens with the red one. Yeah, so it doesn't matter. But you move it down, right? So our curve looks like this. So it's still on the xy plane, and then I take it down by the same by 1 unit, and so the curve is this, lower. And once again, you see the pattern: green cross transforms slowly into it's sort of smoothing out its corner, and becomes a hyperbola, and then the hyperbola becomes a it does change its shape. It's not just shifting; it is changing its shape as it's moving away from this. So, well, one more, I suppose. It's hard to. Like this. So one more hyperbola. Okay, so they hopefully they create a surface. So that's what's supposed to happen in your mind every time you see a graph. You see a map like that. It is the curves are called the level curves. So they correspond to a given level. For each level, there's one curve, even though it might be made of 2 branches. Also, it is hypothetically possible that those curves are not really curves. For example, if the function is constant, then its graph is a horizontal plane, and then if you start crossing a horizontal plane without a horizontal plane, what do you get? You're going to get either nothing or the whole plane. So then your level curve is not a curve; it is a whole plane. Or it could be some kind of chunk of the plane. So level curves or contour curves, depending on the language they use. Even though there is some difference in terminology depending on which do you call contour level curve, this one or that one. Either the one in the xy plane or the one that has been already elevated. And the answer is probably the former. So this is the map of level curves. And once again, it is a thing about the terrain, and each line gives you how you would walk if there is no elevation. So you stay on the same level. It is also discoverable from pictures like that how to identify special points. So this one is this is a settle point. Okay, when you can see how kind of some cross pattern, which does not have to be 90 degrees, and then it could be like this, right? And then you still see a pattern like this. So it's still a settle. So that's one. Then it is a special point. Why we pay attention? Because outside of that point, the behavior is generic. So if I concentrate on this part, look at it. Well, what does it look like? Not much. It doesn't look like much. It is like if you zoom in really in, it will be just a plane, and that's why you have a bunch of lines. You zoom in, those lines will turn into straight lines. So that might be a point, a calculus point to be made, that the level curves become straight lines as you zoom in. Okay, but if you zoom in on this point, that's not going to be, it's not going to be similar. So the, what's going to happen if you zoom in on that point in the middle? What do the level curve look like?
I think they kind of converge on the axes, right?
What do you mean?
I mean, if we consider like a band around the origin and we're zooming in on it,
Yeah.
we can see bits of the parabolas, but the parabolas are oh yeah, sorry, hyperbolas.
Well, they don't have hyperbolas. This is a generic picture, so there's curves that look like hyperbolas, meaning that there might be some asymptotic behavior there. But that's all. So what's the explanation?
Oh, well, I was just thinking that I mean, as we allow the magnitude of z to go to 0, it's like the level curves are they're becoming more and more they're acting like the asymptotes. They look like the asymptotes. Or, sorry, the asymptotes. They look like the axes. Maybe not.
Mm. Well, will it look anything like this? That's the real question. No. In fact, it's going to look like just the same way as it did, because these two lines will remain there. Okay, the angle between them remain there, and so if you zoom in, there will be still some kind of hyperbolic curves here, and the picture doesn't change at all. Okay, so even though the function is very nicely behaved, remember the function we started with is y equal xy, so it's a differentiable, whatever function you can think of. There's nothing wrong with it, but if you zoom in, these special points might produce very unusual behaviors. Seemingly unusual, non-generic, I would say. This is generic, right? And that it behaves like a plane. That does not really behave like a plane. And in fact, even though you can imagine that the curves will not straighten out. That's the big thing. Usually that's what you expect from zooming in. From calculus 1, every curve you zoom in, if it's differentiable, it will give you straight lines, or straight line. And in this particular case, you do have straight lines, but only at some locations, not all. Another situation that we might encounter is kind of a circular level curves, like this. So once again, if you zoom in over here, you're still in the generic situation, right? And but if you zoom in on this point, what's going to happen?
They'll just look the same as the original.
That's right. So they will still have some kind of circular level curves, right? And then you can actually tell me what kind of point is it? What does the graph of a function look like when the level curves look like this?
Is it a cone?
Could be. More generally, what is it? Well, remember, this is one level, that's another level, that's another level, and we're going somewhere. So, what's the word? There's the word from calculus 1.
Is it a solid? Is that
No, presumably the surface will contain a solid underneath it, or if it is a parametric, then inside of it. But no, that's not what I meant. So once again, let me mark the picture is incomplete because there are no markings. So for example, I would write here 10, 20, 30. So these are values of z. That's every time we produce level curves by fixing value of z and plotting the implicit curve f of xy, f of xy equal to, say, 10. Okay, so that's this curve. And then I do the same with 10. And then I do the same with z equal 20. Get the second term, that second one, then the next one. And then that dot, what do you think that dot is? The red. I put it in red, but it's still a level curve. It just happens to be a point. So what is that? What does the graph look like? Well, look at the numbers, 10, 20, 30.
Oh,
What?
are the circles, are the circles getting tighter the farther out we go?
Well, I don't want to say what's happening away from beyond this. So what's happening if we're moving towards well, what am I doing? 10, 20, 30. What am I doing? Suppose I'm a climber.
We're increasing elevation.
Yeah. And at the end, what are we reaching? At the end, the climber has reached what?
Max.
What?
The max.
Yes. This is the maximum. That's all. So maximum. If there are no specific numbers here, it could be a minimum too. But yes, it is in a maximum minimum. So a special point, once again, non-generic point, but it is a maximum. So these are the two main singular points, if you like, of surfaces of function of two variables, either maximum points or saddle points. Even though saddle points might vary, and in fact there is such a thing as a monkey saddle. The regular saddle is, I think that's, I mean, you can have this. So the monkey needs a place for its tail. Okay, so that's why you can possibly have this. Okay, so it's still possible. So what is it? It is unclear. This one is very, very clear. And this one is when time comes, this is the problem that we're going to solve, as just as in calculus 1, and that's optimization problems. Optimization problem, find the maximum value of the function. So instead of function of one variable, we have function of two variables. That's all. So that is really important. And once again, what is the purpose of a saddle point? It is the mess with our solutions. Just like in calculus 1, your derivative equal to 0. Does it mean that it's max or minimum? Yes or no? No, it does not. The answer is the counterexample is x cubed, right? So that's a nasty point. The situation when f prime is equal to 0, and yet it's not neither maximum nor minimum. So it can happen a lot more than that in a function of two variables, and that is a kind of an analog of a saddle point, even though this one is increasing. It is continuing to increase. This one, depending on direction, it might behave up and down or down and up. But it's also a kind of an exceptional situation where the tangent plane. Look at this. If you look carefully, the tangent plane is horizontal, which means that the derivative will be, as we understand, will be 0, and yet it's not maximum or minimum. Okay, so all kinds of combinations might appear, and let me give you an example. This is really not a complicated example. F of x1 for the maximum minimum, say x squared plus y squared. X squared plus y squared is our function of two variables. So once again, we're not going to do the vertical cutting. We're doing horizontal cutting. So we have x squared plus y squared is equal to, say, 1, well, 0. X squared plus y squared is equal to 1. X squared plus y squared is equal to 2, and so on. So well, what are we getting? More implicit equations. Equations of what?
Circles.
Circles. So these are all circles, almost all, except for the first one, which is what? This one?
Point.
It's a point, the origin. Okay, the next one, it has radius 1. The only tricky question is, will they be distributed uniformly or not? And the answer is no. They will be kind of getting close and close to each other. If I'm progressing like I do here, 0, 1, 2, 3, 4, and they will be progressing, they will be enlarging the circles, but not by the same proportion. So if I start with radius 1, then the next one will be square root of 2, right? So the green one, this is radius 1, that's square root of 2, that's square root of 3, and so on. So it will be growing, but slower and slower. And then once again, we'll let me do one more. So x squared plus y squared is equal to 3. So it is a cubic. I'm sorry, the square. No, I'm doing exactly the thing that I promised not to. And that is, this one will be closer. So this square root of 3. Okay, and you can imagine what happens. Well, before we do that, what about negative numbers? Well, the circles turn into a point, and then what point turns into what?
I don't think we have negative numbers, right? Because the sum of two squares has to be non-negative.
Yeah. So what's the curve? What? X squared plus y squared is equal to negative 1. Find all x and y so that satisfy this equation. The answer is
None.
there's none. So empty. The empty set. So there's no curve. And we realize why it is the case. Well, we even realize what's the case. We're cutting our surface with a horizontal plane that lies below the xy plane. It does not cross anything, which means that the whole surface lies above. That's all. And in fact, once you start putting these things together, these things, just like we did, so we take and now elevate each of these in a vertical direction. Okay, so the green one is well, the red one is still on the xy plane. The green one is slightly above. Okay, and then the next one is 2 units above, like this, and then the next one is the other above. So this is so it's like a cup that goes in all directions. It is a surface of revolution. Okay, keep on.